Consider, once more, the timeline of our planet. All 4.5 billion years compressed into a single calendar year. Let us not simply observe this timeline, but feel its passage. January, February. The planet is a newborn, shrouded in fire and steam. It is a violent, chaotic infancy. Through the long month of March, as the world cools, the first, simplest life quietly awakens in the oceans. This is not a grand event, but a subtle, chemical whisper. And then the great stillness begins. For the long spring and the endless summer of this cosmic year, April, May, June, July, August, September, the planet belongs to the microbes. Imagine the sun rising and setting billions of times over a world whose only life is invisible to the naked eye. The days shorten, the moon recedes, the continents drift, and the silent, microbial empire endures. The world slumbers through its long, quiet youth. It is not until mid-November that the great explosion of complex animal life fills the seas. The planet's long autumn has finally arrived. The dinosaurs, those great icons of a lost world, appear very late on Christmas Day. They walk the earth for what seems to us an eternity. Yet their entire reign is but a fleeting holiday week on this calendar, vanishing before the fireworks on New Year's Eve and humanity. Our entire story is a breath in the final second of the year. Every war, every piece of art, every act of love happens in the flicker of the final tick of the clock. Our perception of time, of minutes, of hours, of a lifetime is a scale that becomes meaningless here. Time, in this view, is not something we pass through. It is a physical force, like gravity or pressure, an ocean. And it is in this ocean that any trace of a world before our own would be lost. The first great challenge for its survival is the simple fact that the earth itself forgets. It is a living world, and its lifeblood is change. It is not a static library of stone, but a dynamic system that constantly erases and rewrites its own history. Let us float back now on the deep currents of that ocean, past our own time, past the age of mammals, past the fire and dust of the asteroid that ended the age of dinosaurs. The continents below us drift like sleeping giants, Pangea reassembling in a slow, silent dance. We drift further, beyond the great forests of the Carboniferous, beyond the first fish to walk on land, 400 million years. 440 million years into the deep, deep past. We arrive and settle in the Silurian period. Let us truly immerse ourselves in this ancient moment. The sky above is a different sky. The sun, younger and slightly less luminous. The atmosphere is thinner, less rich in oxygen, and the sky at its zenith would be a deeper, darker, almost violet blue. Weather patterns on this world are vast and slow, without complex topography and vegetation to break them up. Storm systems could grow to the size of continents. Immense cyclones of wind and rain that might last for 1,000 years before finally exhausting themselves. At night, the moon hangs in the sky, visibly larger, closer, and it looks down upon a world of alien constellations. The stars themselves have shifted. The familiar patterns of our own sky dissolved into a new and strange celestial map, and the land. The land is a study in raw geology. Vast shields of ancient, bare granite, gray and pink, polished smooth by winds that have blown for millions of years. Sharp, jagged mountains stand stark against the sky, their peaks freshly born and untouched by the softening influence of soil or life. This is a world without soil. Imagine not dirt, but rock, gravel, and endless plains of fine reddish dust. Planet-spanning dust storms, larger than any we have ever known, would rage for centuries, shrouding half the globe in a dim ochre twilight. The air itself has a different scent, not the smell of damp earth, of decaying leaves, of pollen, but the clean, sharp scent of ozone, the faint, metallic temps of minerals, and the distant, sulphurous breath of a volcano. And the silence. Let us listen to this silence. It is a silence of absence. No bird song, no insect hum, no animal calls, but it is also a silence of presence, the presence of the planet itself. Listen to the low whistle of wind across 1,000,000 square miles of stone. Listen to the rhythmic hush of waves on a shore where no creature has ever left a footprint. Listen to the deep, resonant rumble of the Earth's own inner fire. And listen to the quiet, insistent sound of the world slowly coming apart. The faint crackle of rock, cooling and splitting in the night. The gentle hiss of sand skittering across a stony plain. This is the sound of geology, the sound of time itself. From the edge of these silent continents, you could look out upon the shallow, greenish seas. And here, there is life. The waters are teeming. Trilobites scuttle across the seabed. Strange, armored fish without jaws filter the mud. And giant sea scorpions, some as long as a person, glide through the murky water. All of life's drama, its vibrant, complex dance, is happening beneath the waves. The land is a silent, empty stage, waiting for 1,000,000,000 years of evolution yet to come. Into this ancient, empty world, we place our civilization. For 100,000 years, it thrives, and then it is gone. What happens to its creations? We have considered the slow work of wind and rain, but there are other, even quieter forces of erasure. Consider the simple power of the freeze-thaw cycle. Water seeps into a microscopic crack in a monument of polished stone. During the cold Silurian night, this water freezes. It expands just a little, exerting immense pressure from within. It creates a fracture, a fraction of a millimeter deeper. The next day it thaws. The next night it freezes again. Repeat this process every day for 10,000 years. For 1,000,000 years, the stone is not eroded from the outside. It is wedged apart, silently, inevitably, from within. Near the coastlines, another patient force is at work. Salt weathering. Salty spray from the primordial ocean coats the surfaces of structures. The water evaporates, leaving behind tiny crystals of salt. These crystals grow in the pores of the rock, exerting a slow, steady pressure. The surface of the stone doesn't wash away, but flakes and crumbles, turning to dust in the eternal wind. And the final destination for all this dust, for every particle of a lost city, is the sea. Imagine a single grain of sand, once part of a magnificent sculpture. It is broken free by frost, carried by a gust of wind into a stream, and begins a journey that will last a millennium. It is tumbled against other stones in a riverbed, its edges smoothed, its journey slow. Finally, it is washed into the ocean. It drifts down, slowly, through the dark water, for days, for weeks, until it comes to rest on the abyssal plain, 3 miles beneath the waves. Here, in the crushing pressure and absolute darkness, its journey ends. It is soon covered by another grain of sand, and another. Over millions of years, it is buried under the weight of a continent's worth of eroded memories, compressed, heated, and begins its slow transformation, back into stone. Its original form is not just gone, its very substance has been reclaimed. The library of stone doesn't just lose pages, it grinds them up and uses them to create new ones. We left our single grain of sand, the last echo of a forgotten monument, settling on the deep ocean floor. Buried under miles of water, in utter darkness and silence, it seems to have found a final, peaceful resting place. But on a living planet, there is no final resting place. There's only the next stage of a ceaseless journey. The forces of erasure are not limited to the surface. They are the planet's own heartbeat, its own slow metabolism. The floor of the ocean is not a static foundation. It is a vast, continuous skin of rock, a conveyor belt that is endlessly being born and endlessly being consumed. Picture, in the crushing darkness of the abyss, the mid-ocean ridges. Here, in a silent, slow-motion eruption that lasts for eons, new crust emerges from the planet's inner fire. Molten rock meets freezing water, forming strange, rounded shapes of pillow lava, the newest stone on Earth. This is the beginning of the journey. From its volcanic birth, the new seafloor is pushed outwards, embarking on a pilgrimage that will last for 100 million years. As it travels, it accumulates a delicate diary upon its surface, a constant, gentle rain of marine snow, the shells of microscopic creatures, dust from distant lands. The organic remnants of life in the waters above settles upon it, layer by microscopic layer. The entire history of the ocean, written in fine dust, is laid upon this moving stage. And at the edges of the continents, in the profound depths of the ocean trenches, the journey ends. The ancient seafloor, heavy with time and sediment, gracefully bends and sinks back into the Earth's mantle. This is subduction, a quiet, inexorable surrender. It is not a violent crash, but a slow, deep recycling. The water trapped in the rock is squeezed out, helping to melt the stone above it, fueling distant volcanoes. The rock itself is pulled down into a realm of unimaginable heat and pressure, its substance returned to the slow, churning furnace from which it came. This cycle is the reason why the oceans are, geologically speaking, so young. The average age of the entire ocean floor on Earth today is less than 200 million years. This simple, astounding fact carries a profound implication. In the 440 million years since our hypothetical Silurian civilization vanished, the entire floor of every ocean has been created, has lived its life, and has been completely destroyed, recycled back into the mantle more than twice over. Any evidence resting on it, the foundations of a coastal city, the dust of an inland metropolis, a fossil of a machine wood, have been carried on this conveyor belt to its fiery end. It has been unmade. Its atoms have been reassigned, returned to the planet's heart, to one day, perhaps, be born again as new stone. The library of the ocean floor systematically burns every single one of its books. But what of the continents? They are the great, ancient rafts, thicker and more buoyant, escaping the cycle of subduction. Surely, evidence buried deep within a continent could survive. Here, we encounter a more intimate, more transformative form of erasure, metamorphism. Imagine a shallow sea separating two great continents. For millions of years, it is a calm basin where the sediment of our lost world is gently buried and fossilized. But deep in the earth, the engine of tectonics is at work. The two continents begin to approach one another, their movement imperceptible, no faster than the growth of your fingernails. Over 50 million years, This slow approach closes the ocean. The two landmasses begin to collide. Anything caught in this slow-motion crash is subjected to forces that defy comprehension. The rock is folded like cloth, buried dozens of miles deep. The pressure becomes immense, squeezing the stone with the weight of a world. The temperature rises, not to the point of melting, but to a deep, transformative heat, like a kill that fires for an eternity. Under this intense pressure and heat, the rock's very identity is rewritten. It is metamorphosed. The atoms within its mineral crystals unlock and rearrange themselves into new, more stable structures. The very memory of the rock's formation is being forcibly erased. If there was a fossil in this rock, its shape would be warped, stretched, and smeared into an unrecognizable ghost, a faint streak in the new, flowing bands of the stone. Consider the fossil of a piece of complex technology, a circuit board, perhaps, with its beautiful, ordered geometry. The pressure would crush its structure. The heat would cause its different elements to migrate, to bleed into one another. The silicon, the copper, the gold, they would break their chemical bonds, reforming into meaningless veins of quartz, native metals, and graphite. The story of intelligent design would be overwritten by the simple, brutal story of pressure and heat. The rock's beauty, the elegant swirls of a piece of gneiss, is a testament to the perfect erasure of whatever came before. And this, too, is part of the endless cycle. These metamorphic rocks, born in the roots of a new mountain range, can be pushed upwards over millions of years of uplift. And as soon as they reach the surface, the wind and the rain begin their patient work of wearing them down, carrying their particles once again to the sea to become sediment. The rock cycle is a perfect loop of forgetting. This is the true, staggering depth of the challenge. For a single trace of a lost civilization to reach us from such a deep past, it would have to navigate a nearly impossible gauntlet. First, its remnants would need to find a geological sanctuary, a quiet place, a sedimentary basin on a stable part of a continent known as a craton, that would somehow escape the great cycles of subduction and mountain building for 500 million years. Second, within this sanctuary, it would need to be buried perfectly, preserved in a layer of stone that is never squeezed too hard, never baked too hot. Third, after surviving for hundreds of millions of years in the quiet dark, the rock containing this trace would need to be gently lifted back to the surface, its precious contents intact. And finally, at the end of this epic journey, the forces of erosion would need to expose it at the precise moment in our planet's history when we are here to find it. 1,000 years earlier, it would still be buried. 1,000 years later, it would be dust. To find such a thing is not like finding a needle in a haystack. It is like finding a single, specific, intact crystal of sugar dissolved in an ocean, which is then evaporated into a cloud, rained back down upon a mountain, frozen into a glacier, and then melted into a river, in the hope of tasting its sweetness at the river's mouth. The default state for everything that has ever been made is to be unmade. The preservation of anything from the deep past is not the rule. It is a geological miracle. We have journeyed through the great planetary forgetting. We have come to understand that to look for a city of stone from a time before the mountains we know were born is to look for a whisper in a thunderstorm. The earth is too alive, too dynamic. It recycles its own memories. So we must learn to listen in a different way. Our search shifts from the realm of archaeology to the realm of planetary forensics. We are no longer looking for an object, a tool, a monument. We are looking for an echo. We are searching for the chemical ghost that a global, energy-intensive civilization would leave behind, imprinted upon the very chemistry of the planet itself. Imagine the Earth as a living organism. To understand its deep past, we cannot simply observe its surface. We must look at its geological bloodwork. We must search for the faint anomalies in the layers of stone that speak of a time when the organism was out of balance, a time when it was experiencing a strange industrial fever. Let us begin with the most fundamental element of life and of industry, carbon. For eons, the Earth maintained a slow, rhythmic breath, the great carbon cycle. Consider the world of the Silurian period. Vast, shallow oceans bloom with trillions of tiny plankton, each one a microscopic engine, breathing in the carbon dioxide from the atmosphere, using the sun's energy to build its tiny shell or body. This is the foundation of everything. When these organisms perish, most of their carbon is recycled by other life forms, but a tiny fraction is not. It sinks into the oxygen-poor mud of the deep sea floor. Over millions of years, this accumulated carbon is buried, compressed, and cooked by the Earth's inner heat. It is slowly transformed into the vast, dark reserves of what we call fossil fuels. Think of it as a planetary savings account of ancient sunlight, a battery charged over an almost unimaginable span of time. For hundreds of millions of years, the planet made slow, steady deposits into this account, creating a world in equilibrium. The geological record keeps a meticulous ledger of this balance. Ancient limestone, formed from the calcium carbonate shells of those marine creatures, is a library of the ancient oceans, and in it we can read a subtle chemical story. Nature uses different isotopes of carbon atoms of the same element, but with slightly different weights, and life, in its quiet efficiency, shows a distinct preference for the lighter form. Carbon wealth. It is energetically easier for the enzymes of life to capture and use. This subtle preference, multiplied by trillions upon trillions of organisms over the course of the Earth's history, means that all living things and the fossil fuels they become are enriched with this lighter carbon. So, for hundreds of millions of years, the rock record shows a steady, predictable ratio of light to heavy carbon. It is the background rhythm of a healthy, breathing planet. Now, imagine an industrial civilization rises in this ancient world. It is clever. It discovers this immense planetary battery, this buried sunlight. It learns to drill and to mine, to extract this ancient carbon and burn it for energy. In doing so, in what is a mere instant of geological time, a few thousand years, perhaps it takes the accumulated savings of 300 million years of stored carbon and releases it back into the atmosphere in a great, invisible flood. The entire planet's breath is thrown out of rhythm. This sudden, massive influx of light, life-preferred carbon changes the chemistry of the atmosphere. The oceans, the planet's great chemical flywheel, absorb much of this excess carbon, and in doing so, their own chemistry begins to change. And this is where the permanent record is made. The tiny organisms floating in the sunlit layers of the Setha foraminifera, the coccolithophores, continue to build their shells. But now, the water they live in is saturated with this anomalous light carbon, and so their shells are built from it. When they die, they sink to the seafloor in a constant, silent rain, and they form a new layer of sediment, a layer that is, from a chemical perspective, utterly different from the 10,000 layers that came before it. Imagine yourself as a geologist, 440 million years in the future. You drill a deep core from an ancient, undisturbed seabed. You analyze the carbon isotopes, layer by layer. For 1,000 feet of your core, the data is stable, a gentle, oscillating line on your screen showing the normal rhythm of the ages. And then, suddenly, in a band of rock just a few inches thick, the line plummets. A sudden, violent, and massive spike of light carbon appears, lasts for a brief period, and then slowly, over the next several feet of rock, returns to the old rhythm. This is the signature. It is unambiguous. It tells of a moment when the planetary savings account was emptied, when the ancient sunlight was released in a flash. It is the fossil fuel fingerprint of a lost industrial world. And this fingerprint would have a partner, a corroborating echo. The great release of carbon would have warmed the planet. As the oceans warm, they hold less dissolved oxygen. This, combined with nutrient runoff from the civilization's activities, would create vast dead zones in the ocean. Picture these ancient seas. The surface might still teem with life, but in the depths, the water becomes still, stagnant, and starved of oxygen. The normal cycle of life and death is broken. The gentle rain of organic matter that falls from above is no longer consumed by scavengers. It simply accumulates on the seabed in a thick, dark, undisturbed blanket of organic mud. Over millions of years, this mud, rich with the undecayed carbon of a dead ocean, is compressed into a very specific type of rock, black shale. This rock is often finely laminated, with paper-thin layers that tell of seasons and years passing in a world without disturbance, a world without breath. So, a geologist finding that sharp carbon spike in the limestone would look for its partner, and they might find it, a sudden, globally distributed layer of black shale, a fossil of a sick ocean. The limestone anomaly would tell us what happened, a colossal release of buried carbon. The black shale would tell us how the planet responded, with a fever and a struggle to breathe. Together, they would form a single, powerful story. Not a story of cities or kings, but the story of a planetary metabolism, a global system pushed violently out of balance. This is the nature of the ghost we are hunting. We have considered the great metabolic signatures of a civilization, the global fever recorded in carbon, and the planetary suffocation recorded in black shale. These are the signs of a world's relationship with energy. But an advanced civilization does not only consume energy, it creates, it designs, it synthesizes. It brings into existence materials and substances that nature, in its 4.5 billion years of patient experimentation, had never conceived. These unnatural materials, these technofossils, would form the next layer of our search. They would be the fingerprints not of a planetary metabolism, but of a planetary mind. Consider the world of synthetic polymers, the family of materials we call plastics. To us, they are mundane. To the planet, they are an utter novelty. They are immensely long chains of carbon and hydrogen atoms, linked together in strong, resilient, and highly ordered patterns. Patterns that do not arise from the chaotic tumble of natural chemistry. They are a signature of intention. Now, imagine our ancient Silurian civilization creates such materials. They become ubiquitous. They are used for everything. And then, the civilization vanishes. What happens to the trillions of tons of these synthetic polymers left behind? Let us follow the journey of a single, discarded object made of this material. It lies on the barren, rocky ground. It does not rot. The microbes of its time have no evolutionary toolkit to digest these strange alien molecules. The sun's ultraviolet radiation might slowly make it brittle, but its fundamental substance remains. A rainstorm, one that lasts a century, washes it into a river. The river carries it to the sea. For thousands of years, it floats in the vast, shallow oceans, slowly breaking apart under the sun and the waves. It does not decompose back into simple, natural elements. It fragments. It becomes a million smaller pieces, then a billion, then a trillion. It becomes a cloud of microscopic, synthetic dust suspended in the water column. This dust, these microplastics, would join the natural rain of marine snow. They would be ingested by trilobites and filter feeders, entering the food web. But ultimately, they would settle everywhere on the bottom of the ocean. From the shallow coasts to the deepest abyssal plains, a new and unnatural ingredient would be added to the sediment. Over millions of years, as this sediment is compressed into rock, these synthetic particles would be trapped within it. Imagine a future geologist examining a piece of mudstone from this era. Under a powerful microscope, they might see scattered among the natural clay and fossil fragments these strange, unnaturally uniform particles. Perhaps they would form a new kind of rock, a conglomerate with a synthetic matrix, a material that future geologists might call plastistone. But even this is not the deepest signature. As this rock is buried further, subjected to the gentle heat and pressure of the deep crust, the plastic particles themselves would degrade. Their complex structures would break down, but they would not vanish completely. They would leave behind a chemical ghost, a molecular fossil. The long-chain hydrocarbon molecules, so alien to nature, would leave a distinct chemical residue, a stain of complexity in the rock. A future scientist, using a technique like pyrolysis gas chromatography, could analyze the vapors released when heating a piece of this ancient shale, and they might find, among all the natural organic compounds, the unmistakable signature of the thermal breakdown of polyethylene or polystyrene or some other complex polymer. It would be the chemical equivalent of finding a perfect, laser-etched cube in a world of naturally weathered stones. It would be an undeniable sign of artificiality. Next, let us consider the quiet foundation of any large-scale civilization, agriculture. To feed billions, you must overcome one of nature's most fundamental limits, the availability of nitrogen. The air we breathe is mostly nitrogen, but it exists in a form that is incredibly stable and difficult for life to use. It is a vast, locked reservoir. In the natural world, only two things can effectively fix this atmospheric nitrogen into a usable form for plants: the immense energy of a lightning strike and the patient work of certain specialized microbes. This natural process is a slow, steady trickle, and it governs the productivity of the entire biosphere. An advanced civilization would inevitably learn to bypass this limit. They would invent an industrial process to seize the power of lightning, to take nitrogen from the air and convert it into ammonia, the foundation of synthetic fertilizer. They would learn to feed themselves from the sky. This act would represent a fundamental rewriting of a planetary cycle. The sudden, massive flood of new, usable nitrogen into the biosphere would be a shock to the system. This fertilizer would run off their farms, into the rivers, and out into the oceans. It would trigger immense, planet-spanning algae blooms, which would die, sink, and further contribute to the oxygen-starved dead zones we have already discussed. and it too would leave a fingerprint. The nitrogen produced by an industrial process has a different isotopic signature from the nitrogen fixed by microbes. A future scientist analyzing the nitrogen isotopes preserved in the organic matter of our layer of black shale would see a dramatic and sudden shift, a deviation that speaks of a time when the natural trickle of nitrogen was overwhelmed by an industrial flood. It would be the fossil of a global farm, a quiet chemical testament to a civilization that had learned to command the elements to feed its people. Finally, we arrive at the most profound, the most unambiguous, and perhaps the most haunting signature of all. The one that speaks of a civilization that has unlocked the deepest secrets of matter, a nuclear signature. In nature, on Earth, elements heavier than uranium are virtually non-existent. They are forged only in the most violent and energetic events the cosmos has to offer, the collision of neutron stars. The primordial supply of these elements that seeded our planet during its formation have half-lives so short that they have long since decayed into nothingness. A civilization that learns to split the atom, however, begins to create these elements anew. They learn to transmute one element into another. They learn to wield the stellar fire, whether for energy or for weapons or for science. Their nuclear processes would create a host of new artificial isotopes. Most of these would be short-lived, but a few are exceptionally stable. Consider an isotope like plutonium-244. It has a half-life of 80.8 million years, or curium-247, with a half-life of 15.6 million years. In the 440 million years since our hypothetical civilization, these isotopes would have undergone many half-lives. A deposit of curium-247 would be gone. A deposit of plutonium-244 would be reduced to less than 2% of its original amount. But it would not be zero, and more importantly, as it decayed, it would produce a cascade of other, very specific, daughter isotopes, creating a unique and anomalous ratio of rare earth elements that has no natural explanation. To find a concentrated layer of these specific elements and their decay products in the geological record would be a staggering discovery. It is different from all the other signatures. A carbon spike could, a skeptical scientist might argue, be the result of a truly bizarre and unprecedented episode of global volcanism. But there is no known natural process that can create and concentrate plutonium-244 in the Earth's crust. It is a purely artificial signal, a fingerprint that says, "We were here. We rearranged the heart of matter. We understood the atom." It is the closest thing to an intentional message, a note in a bottle thrown into the deepest part of the ocean of time. And so, the true signature of a lost industrial world would not be a single artifact. It would be a thin, global layer in the strata of the Earth, a ghost layer, a boundary in the rock that tells a story of a time of profound and rapid change, a story written in a cocktail of strange chemistry, a sudden shift in carbon, a depletion of oxygen, the molecular fossils of plastics, an anomaly in nitrogen, and the faint, unmistakable, radioactive glow of man-made stars. In our journey so far, we have built a theoretical toolkit for a search that seems almost impossible. We have moved beyond the search for tangible objects and learned, instead, to listen for the faint, chemical whispers of a lost industrial age. The anomalous carbon, the oxygen-starved seas, the molecular fossils, the man-made atoms. We have wandered through this hall of possibilities as a private thought experiment. But this raises a natural and compelling question. Is this a lonely walk? Or have others, within the formal halls of science, ever paused to ask such a profound and unsettling question? Could we be so blind to our own planet's history that an entire chapter, an industrial saga, might be missing from the book? The answer, remarkably, is yes. The question has been asked, and the story of how it was asked is as fascinating as the question itself. It required a convergence of two vast and different perspectives. Imagine looking at the Earth from two opposite directions. One is the view from the stars, looking down. The other is the view from the stone, looking up through time. The view from the stars belongs to the astrophysicist Adam Frank. His work involves thinking about life across the cosmos, on distant exoplanets. He contemplates how a civilization on another world might reveal itself across interstellar distances. They wouldn't send a message, they would alter their planet. Their industries would change their atmosphere. Their technology might alter the light reflected from their world. An astrophysicist learns to see a civilization as a planetary phenomenon, a force of nature that leaves a detectable trace on its home. The view from the stone belongs to the climatologist Gavin Schmidt. As the director of NASA's Goddard Institute, his work involves looking deep into Earth's own past. He reads the subtle language of ice cores and deep-sea sediments to understand the great climate shifts of ancient eras. He understands the Earth as a dynamic breathing system that has existed in many different states. And he knows how the planet keeps its records and, as we have seen, how it erases them. The Silurian Hypothesis was born where these two perspectives met. The astrophysicist's question, what would an alien civilization look like, was turned inward, applied to our own world. And the climatologist provided the crucial knowledge of the archive, the geological record, to know what kind of signature could possibly last for eons. Together, they authored a paper that gave a formal name to our quiet meditation, the Silurian Hypothesis. Would it be possible to detect an industrial civilization in the geological record? The name itself is a gentle clue to the spirit of the inquiry. It is not a claim that they believe a civilization of ancient trilobites existed in the Silurian period, 440 million years ago. The name is a thoughtful and charming nod to a classic story from the British science fiction series, Doctor Who. In the story, an intelligent reptilian species, also called the Silurians, had an advanced civilization on Earth that predated humanity by hundreds of millions of years. By choosing this name, Frank and Schmidt were being clear about their intention. They were signaling that they were stepping, deliberately, onto the boundary between known science and profound speculation. It was an act of intellectual humility, an admission that our knowledge of our own planet's history is incomplete. Their goal was not to prove that the Silurians existed, but to ask, how good are we really at reading the book of the Earth? How would we even know if a chapter was missing? The core premise of their hypothesis is the very journey we have just taken. They begin with the sober understanding that any direct physical evidence would be long gone. After 100 million years of rain, wind, continental drift, and subduction, the chance of finding a fossilized city is effectively zero. So, what would survive? They concluded, as we have, that one must search for the indirect, global, geochemical evidence. To build a template for what to look for, they turned to the only example of an industrial civilization we have ever known, our own. They looked at the planetary scale changes happening right now in this proposed era of the Anthropocene, the age of humans. Let us pause here and consider this for a moment. Imagine yourself as a geologist. A billion years from now, you are studying the rock layers from our distant past. You drill a core, and you come to a thin, dark, chaotic line in the strata. This is our time. This is our legacy. In this thin layer, your instruments would detect a sudden, violent spike in light carbon isotopes, the chemical signature of our fossil fuels. You would see a corresponding layer of dark shale, a sign of sick, oxygen-depleted oceans. You would find the strange, unnatural molecular fossils of our plastics, molecules of a complexity nature never produced. You would detect a massive anomaly in the nitrogen isotopes, the ghost of our global agricultural system. And, if your instruments were sensitive enough, you might detect the faintest radioactive trace of elements that have no business being in the Earth's crust, the final, fading echo of our mastery over the atom. This chaotic, chemical smear in the rock, this is our ghost. Frank and Schmidt used this ghost, our ghost, as the blueprint. They catalogued the fingerprints we are leaving in the present to create a search template for a similar event in the deep past. This reframes the entire exercise in a humbling and deeply introspective light. The search for a precursor civilization is not about finding alien monsters. It is about holding up a mirror that reflects our own transient existence, our own fleeting moment of immense power, and the quiet, subtle, and perhaps eternal mark we will leave upon the silent library of stone. With this carefully assembled chemical blueprint in hand, the ghost image of our own industrial era, the Anthropocene, Adam Frank and Gavin Schmidt turned to the great stone archive of the Earth. The question was no longer theoretical, it was practical. Is there a chapter anywhere in the hundreds of millions of years of the geological record that tells a similar story? Is there a previous moment when the planet suffered a similar, rapid, and global fever? The search is not a simple one. The Earth's history is filled with dramatic events. There have been times of immense volcanism, times of rapid cooling and warming, times when the oceans changed their chemistry. The challenge is to find an event that has not just the right kind of change, but the right speed and character to match the fingerprint of an industrial civilization. In the long history of the planet, one event in particular stands out as an especially compelling candidate for investigation. It is not an obscure event, but one of the most intensely studied and mysterious climate phenomena in Earth's history. It happened approximately 56 million years ago at the boundary between two geological epochs. It is called the Paleocene thermal maximum, or the PETM for short. Let us travel to this world for a moment. 10 million years have passed since the demise of the dinosaurs. Mammals, our own distant ancestors, are rapidly diversifying, filling the empty niches the giants left behind. The world is already a warm, greenhouse place, likely with no permanent ice caps at the poles. The continents are in a more recognizable, yet still alien, arrangement. Into this already warm world, the PETM erupts with sudden and dramatic force. Over a geologically short period, a colossal amount of carbon, thousands of billions of tons, is released into the atmosphere and oceans. As a result, global temperatures spike by an additional 5 to 8 degrees Celsius. The Arctic becomes a subtropical swamp, with water temperatures resembling a warm swimming pool. The oceans absorb so much carbon dioxide that they become acidic. This acidification has a devastating effect on marine life. countless species of deep-sea organisms with calcium carbonate shells. The very same organisms that provide us with the isotope records vanish from the fossil record. It was a mass extinction event in the deep sea. The entire event, from the initial carbon release to the slow return to normal conditions, lasted for nearly 200,000 years. As geologists began to study this event in detail, they found a series of signatures that are an eerie echo of our theoretical fingerprint. First and foremost was the carbon. The PETM is marked by a massive negative carbon isotope excursion, exactly the kind of sharp shift towards lighter, life-preferred carbon that we identified as the key indicator of fossil fuel burning. The resemblance to the potential geological fingerprint of the Anthropocene is striking. It is a geological ghost story. Then there was the planet's response. The evidence for ocean acidification and widespread anoxia oxygen-starved zones recorded in the sediments as dark, organic-rich layers matched perfectly with the secondary echo we had anticipated. It was the signature of a planet struggling with a sudden climate crisis. So here it was. An event in the deep past with a carbon isotope signal uncannily like our own, and a planetary response to match. It was the most compelling candidate in the entire geological archive. Could this be the remnant of a forgotten industrial age? This is where the crucial question of timescale comes into play. The subtle but all-important variable. Though the PETM was rapid in geological terms, what does that truly mean? As scientists examined the layers of sediment that recorded this event with higher and higher resolution, they were able to estimate the duration of the initial carbon release. And here, the analogy breaks down. Our current carbon release, the one driving the Anthropocene, is not happening over millennia. It is happening over centuries. Geologically, the difference is immense. The PETMA release is a steep slope. Our release is a vertical wall. It is the difference between a planet's slow, deep sigh and a sudden, sharp cough. This discrepancy in speed points strongly towards a natural, though dramatic, cause for the PETM. The leading theory suggests massive volcanic eruptions in the North Atlantic cooked vast underground deposits of coal and oil, triggering a runaway reaction that released frozen methane from the seafloor. So, the PETM was likely not the Silurians, but the failure to find a lost civilization is perhaps the most profound point of the hypothesis. The true value of the PETM is not in what it could be, but in what it shows us. It is a case study. It shows us how the planet responds to a large-scale carbon release. It shows us the cascade of effects: warming, acidification, extinction, and it shows us that it takes the Earth system nearly 200,000 years to recover from such a shock and find its equilibrium again. It is a warning, etched in stone, from 56 million years ago. And this brings us to the true, philosophical conclusion of the Silurian Hypothesis. The goal was never really to find lost worlds or reptilian ancestors. The goal was to hold up a mirror by asking if we could detect a prior civilization. We are forced to ask the question: how will our own civilization be seen in 10, 50, or 100 million years? The hypothesis teaches us that our presence on this planet will not be recorded in our grand cities or our complex machines. It will be recorded in the thin, chemically disturbed layer of rock we leave behind. The PETMES shows us what a fast, natural event looks like. And in comparison, it highlights that our own event, the Anthropocene, is geologically almost instantaneous, perhaps unprecedented in the planet's history. The search for others ultimately reveals ourselves. The search for a ghost in the geological machine makes us realize that we are the ghost being created. The geological archive may not hold stories of other civilizations, but it holds deep lessons about the consequences of planetary change. And in searching for others and finding only the echoes of natural cycles and ancient fevers, we are left with a deeper understanding of our own unique, fleeting, and profound role in this present moment. Our long journey is coming to an end. We began with a question, a captivating whisper of what if. We searched for a lost civilization in the 440 million year old rock of the Silurian period. We learned that any city of stone would have been turned to dust, its dust washed to the sea, its seafloor pulled into the fire of the mantle. We understood that the planet itself is a machine for forgetting. So, we changed our search. We looked not for a body, but for a ghost, a chemical signature. And we found that such a signature would be a profound, planetary-scale disruption. A story written in atoms. And then we turned to the Earth's great stone library and looked for such a story. In the profound silence of the geological record, we found no clear chapter that spoke of another industrial age. We found ancient fevers, like the PETM, born of the planet's own powerful natural cycles. But we found no unambiguous whisper of another mind, another forge, another industrial heart beating in the deep past. The silence in the rock is, perhaps, the answer we were seeking. The most likely, the most sober conclusion is that this has not happened before. That in 4.5 billion years of solar days and lunar nights, the particular confluence of events that led to a species like ours, a species that could not only think, but build and burn and reshape a world on a global scale, has only happened this once. There is a profound weight in this silence, a sense of solitude, but it is not a lonely solitude. It is a precious one. It reframes our existence. We are not just another iteration in a long, repeating story. We are, as far as we can tell, a planetary first. Let your mind drift back one last time to the cosmic calendar. See the entire history of the world as a great, slow-flowing river of time. For most of its course, the river is clear. It reflects the slow dance of geology and the quiet, patient evolution of life. We see the long, slow summer of the microbes, the autumn of the strange sea creatures, the brief, dramatic holiday of the dinosaurs. And then, in the final flicker of the final second of the year, a single, brilliant, and impossibly bright flash of light appears on the surface of the water. That is us, our Anthropocene. From this great distance of time, it is not a tragedy. It is not a scar. It is a spectacle. It is the signature of a planet, after 4.5 billion years, finally developing a part of itself that could look back upon the river and wonder where it came from. For a brief, brilliant moment, the planet woke up. The legacy we are creating, the thin ghost layer we will leave in the rock, is the record of that awakening. A future intelligence, whether it evolves on Earth in a distant eon or arrives from a distant star, may never know our names. They will not hear our music or read our poetry. They will not understand our philosophies of love or loss or hope. But as they analyze that thin, dark line in the strata, they will know something profound. They will know from the carbon isotopes that a form of life learned to unlock the ancient, buried sunlight of a star that had set 500 million years before. They will know from the molecular fossils that a form of life learned to create new kinds of matter, weaving atoms together into patterns that nature itself had never attempted. They will know from the nitrogen signature that a form of life learned to seize the lightning from the sky to feed itself, transcending the natural limits of its world. And they will know from the faintest radioactive glow that for one brief, astonishing moment, a form of life on this small blue planet learned the secret of the stars themselves. This is the story we are writing in stone. It is not the story of our hearts. It is the story of our hands and our minds. It is the testament to our restless, curious, and powerful nature. And so, we end where we began, in the quiet dark. The silence of deep time is all around us. It is not an empty silence. It is a silence full of perspective, full of peace. The weight of our daily lives, our worries, our fears, they all find their proper scale against the backdrop of this immense, patient history. Our lives are a brief and beautiful flash. Our civilization, a fleeting, brilliant dream. This small planet has spun in the silent darkness of space for a very, very long time. And it will continue to spin long after our ghost layer has settled and turned to stone. The wind will still whisper over the rocks, the rain will still fall, the continents will continue their slow and silent dance. Our transience is not a reason for sadness. It is the very thing that gives our moment its beauty and its meaning. We are a brief, complex, and wondrous pattern in the grand, slow, and mysterious unfolding of the cosmos. A fleeting thought in the mind of the universe. And now, it is time to let that thought go. It is time to let the river of time carry you gently into the quiet darkness. It is time to rest.